That's why I didn't use those.
You're recording.
Yeah, are his
It's going right now.
are his exams like are the questions in sections kind of like no they're just kind of all you
It's like
can
all
have
around.
volcano one here, volcano one there.
Yeah, that one's just right there.
Thank you.
Like, I did understand people, but like, when you respond to questions, and they always thought that I couldn't understand what I just didn't want to. But I like translate my response to Dr. Everything. It just takes that much longer for me. I didn't understand it. It worked out great, though. Oh, Japan.
Jenna, I'm going to ask you to check the screen every once in a while.
Okay.
Does it have the entire
Yeah.
page now?
Japanese, I speak
It is.
English. And who would, you know, there was some.
And is it recording? Is it recording?
Yeah.
Yes, the red.
All right, perfect.
Because I didn't know how to say it in English. Thank you. It was
All right. Hello, everyone. So I figured out the number of people. It's not too bad. So one announcement, I will be extending the deadline for homework 3 to next Thursday. I believe right now it's set to be Monday or Tuesday. Tuesday. So I'm going to extend it to Thursday. Does that leave enough time for you to finish? Okay, perfect. I can be flexible on that, but I don't want to, because I'm going to assign the next homework soon, and I don't want it to pile up with the other ones. So that's kind of what I'm trying to avoid. But let's try to finish it by Thursday, and then if for any reason you can't do it, then we can discuss it on next Tuesday or Thursday to see if we need to extend it maybe a day. But for now, let's set it to Thursday, and I'll send an email to the class to let them know. Any question? Yeah.
Just a general question from the homework. Are we gonna, there's a portion of it that seems like it is review material, and the second question where you're breaking it up into sub-layers to calculate the effective stress and consolidation of those layers. Are we gonna be reviewing that as a class, or is that something that we need to just review on its own?
I expect that you reviewed that on your own. So that part is related to the consolidation class in soil mechanics, and I'll get to that in today's class, and I'll show you the part that I want you to review, and you can use the homework assignment that I uploaded on D2L under soil mechanics notes as a guide to help you go through that part of the homework 3. But I rely on you to review that part. Yes.
From last class, I was getting a little confused. For flexible footing, is it when the stiffness of the footing is less than the stiffness of the soil?
That's a good question. There isn't a really good answer to that of what less is. It's not when the stiffness is less than the soil stiffness. The stiffness of the footing, the foundation, whatever material it is, whether if it's concrete, steel, wood, foundations are usually concrete, but in some cases might be made from other material. Whatever it is, it's going to have a higher stiffness compared to the soil. The question is how high that stiffness is compared to the soil. If it's really high, then it acts as a rigid foundation. But if it's somewhere closer to the stiffness of the soil or rock, then it is considered as flexible. So for example, if you're building a foundation on sands and clays are relatively softer, so that concrete foundation will act as a rigid foundation. But if you're building a concrete, the same concrete foundation on top of rock, which we do a lot of times when we build bridge foundations. We want to get down to the bedrock, not to put the foundation on the soil, but we want to dig and excavate enough to get to the bedrock. In those cases, the stiffness of concrete compared to the stiffness of rock are pretty comparable, and in that case, the foundation acts as a flexible foundation. So it's really a relative, the relative ratio of these stiffnesses.
And there's no set, like, number, or we can't really say, like, relative is kind of vague.
Relative is kind of vague, and
There's
it's,
no, like, distinct line you can put there, where this is, everything above this is.
Yeah. I think there are some numbers based on older closed form solutions. I can tell you that in our profession, our ability to do numerical analysis is increasing because the softwares are getting cheaper, the computers are getting faster. So we tend to do a lot more numerical analysis compared to what our previous engineers did 20, 30 years ago, which was a lot of charts and graphs and closed form solutions. So in those closed form solution examples, there were some limits that, if the limit is between such and such, you're a flexible foundation. If it's above such and such, it's rigid foundation. But nowadays, we can easily implement it in Excel or use these commercial software or finite element, finite difference programs that we can model it precisely and know whether it's flexible or rigid. So just one example for that, I was, and we do that quite often. I was working on a bridge project in Canada where we had to design the foundation, and the foundation was supposed to be, there were two types of foundations: deep foundations, piles that were going to be drilled into rock, and then footings, giant 4 by 5 meter with almost half a meter to 1 meter thickness footings sitting on bedrock. And we originally started assuming rigid foundations, and then the client, the structural engineers, came back and said, well, you're making this assumption, it's conservative, but in the seismic studies, it may not necessarily be conservative. And you can easily switch back and do the calculation based on rigid foundation. In our case, it turned out that for a 4 by 5 meter with 1 meter thickness concrete sitting on the type of rock that we had on eastern side of Canada, which rock tends to get a lot stiffer as you go towards the east versus the west. In that case, that foundation turned out to be flexible because the rock was so stiff. So to give you a short answer, there are limits, but I don't have it off the top of my head, and we tend to not really use them these days. Any other question about the material in previous class? So Milad, I believe he covered until page 9. Is that, can you confirm that?
Yes.
Through page 9? So including page 9?
Yeah, he covered page 9.
He did cover, okay, perfect. So what I'm going to do today, we have a 3-hour class. We're going to take we're going to go for an hour and 15 minutes until 12:30, and we get a 15-minute break if you want to get a bite or something, and then we continue until 2. Yeah. So what I'm going to do today is to finish the handouts week number 3, which is the foundation settlements, and then after that I'll start the bearing capacity of foundations. Okay. Any question or comment? So again, the homework 2, I'll post the solutions for homework 2 today at 4. And to give you a chance for those of you weren't able to submit, you still have time until 4 p.m. today to submit with 50% deduction. And then I'll assign the next homework. And homework 3 will be extended to next Thursday. And then I'll, either today or next Tuesday, I'll assign the next homework 4. Okay? Alright, so let's go to page 10 of handout week 3. I think I might have to zoom in a little bit. And Jenna, can you check that? Let me push this out. Can you please check that the screen is covered?
It's covered, but I don't know if you could read.
Oh, you may not be. Okay, so let me do this. Let me zoom in more to just one side.
Yeah, I think that's good.
It's better.
Yeah.
Okay. All right. So, page 10, settlement of shallow foundations on sands. And I'm just going to quickly go over the remaining pages to give you an idea of what the outline of the class is. So we have the settlements on foundations on sand, and that goes through page 11, 12, 13, 14. And then on page 16, we get the settlement of shallow foundations on clay. And the settlements in clays are divided into 2 sections, the immediate settlements and the consolidation settlements. The material on page 16, 17, 18, and 19 are for the immediate settlement of foundations on clay. And then starting page 20 is the part that I want you to review on your own, which is on the consolidation settlement. And that goes through page 20, 21, 22, 23, 24, 25, 26. So if you remember on 26, we had all these case 1, case 2, and then on page 27, we have the case 3 in our soil mechanics class. These are basically reviewed. And then, so I'll ask you to review this on your own. And then on page 28, there is a section that I'll start covering in this class, and that's the modifications that we have to do for 3-dimensional settlements. Because the stuff that we discussed in soil mechanics are all 1-dimensional settlements. Now we want to see what happens underneath a building where we get a 3-dimensional settlement and dissipation of the flow water pressure, and how that affects the amount of settlement. So there is a little piece on page 28 and 29 on 3-dimensional settlement that I'll cover as part of this course. So let's go back to page 10. And it's on the settlement of foundations on sand. Now I want you to, for a second, go back to the equation that we had for elastic solution. And maybe flip back through your notes and let me know if you can spot the equation, the general equation for elastic solutions. Let me know the page number. Oh, here it is. So page 6. General form of equation based on elastic solution. So when we say elastic solution, it means that we don't care about sand or clay or any other material. It could be steel, concrete, anything. That's how the form of equation is developed. And I want you to look at the components in this equation. So the settlements is a function of QB, that's our load. So if you increase the load, the settlement increases, that's obvious. Then we have B, which is the dimension of the footing in the denominator. That's a little counterintuitive, because you think that if I'm increasing the dimension of the footing, why would my settlement increase? Well, the reason is that if you increase the dimension of the footing and keep the QB, the stress, the same, your total load will increase with the square root of the dimension. So you're increasing the dimension, but your total load is increasing more than your dimension is increasing, and that results in the increase in settlement. Is that kind of clear? Yeah. That B being in the denominator is something that usually confuses people. And then there is elastic modulus in the denominator. So if the elastic modulus increases, the foundation settlement decreases. Let me first ask the question, what elastic modulus this refers to? Is it the soil or the foundation?
Soil.
It's the soil. It's the elastic modulus of the soil. Let me make a small note on that. There is really nothing here on the stiffness of the foundation, except the fact that when we get to the flexible and rigid footings and the settlement at the center and corners, that's where the stiffness of foundation comes into play. But in terms of the settlements in general, that's just the elastic modulus of the soil. And then there are those two other factors, I1 and I2, and depending on whether if you're using the sand equations or clay equations, whether if it's a circular footing or the rectangular footing that I've discussed on the following 2 pages, these influence factors may be named something else. So they may be called I1 and I2, as you see in this general equation, or they may be called, let's see, if you flip to the next page. So do you mind sitting somewhere else, because we're recording? Make sure we don't. Okay, that should be good. So if you flip to page 7, you see there is an I sub z. So instead of I1 or I2, it's just I sub z. If you look at page 8 for the settlements for a rectangular footing, you see the same components. There's a QB, there's a B in the denominator, there's a elastic modulus in the denominator, and then there's an I factor there, and 1 minus nu squared, nu being Poisson's ratio. So those variables are always there, QB, B, elastic modulus, and rest of them are these modifiers that depend on the shape of the footing, depend on the depth of the bedrock, depend on the Poisson's ratio of your soil. So all these other factors are lumped into these other influence factors, or I factors. Now I'm going to go back to page 6 and look at that general equation. So the load, foundation, dimension, elastic modulus, and some other factors. Now, your load is given. The structural engineer gives you the load. The foundation dimension is also set. You're trying to design a foundation. You make an assumption on the foundation dimension. You say, I want to check to see if the foundation with the size of 2 feet by 4 feet is going to work. So that is set. The influence factors are important, but not that important. But there is one factor that is very important, and that's the elastic modulus of the soil. So it turns out to be something that is very difficult to measure to or estimate to. So if you measure your elastic modulus to be 2 times higher or 2 times lower, your settlement will be directly changed. Will be directly influenced by that, by your estimate on elastic modulus. So knowing the importance of elastic modulus, and again to emphasize, this is the elastic modulus of the soil or rock or whatever is underneath your foundation. Knowing the importance of that, now I'm going to go back to page 10 and read the first bullet item. We can use the elastic equations described above, that's on page 6. the main input parameters in the above equation is the elastic modulus. So what we need to do if you have a foundation sitting on sand is to estimate the elastic modulus of that sand. Now it turns out to be, it's easy to say, but it's very difficult to do. And part of the reason is that sands are they cohesionless or cohesive or cohesionless? Cohesionless. They're granular, cohesionless soils, right? Granular, cohesionless soils are stress dependent or stress independent. Before you answer, let me step back and go back to week 1. We started with soil strength, right? And we said the soil strength is defined by the strength of the soil is equal to C plus tan of phi times stress, normal stress, times sigma, right? For clays, phi angle was 0, so the strength is just a solid line. I'm gonna draw it here. So this is the strength of soil, and this is sigma, or sigma prime. And we said that the general form of the strength, so this is failure on a failure plane, or the strength of the soil is C prime, this is C prime, and this is the angle phi prime. So that's C prime plus sigma prime multiplied by tan of phi prime. Now in sands, C prime is 0, so your behavior is only governed by phi prime, or the friction angle, which means if your sigma prime increases, your soil strength also increases. That basically means that sands are stress dependent. So if you're looking at a sand underneath 1 meter of soil, at depth 1 meter, it behaves differently than a sand that is under 10 meters of soil, because sigma prime at that depth is different. For clays, it's otherwise. For clays, we write it usually in a form of tau ff is equal to just Cu, and this whole term disappears. So it just becomes a constant that is not related to sigma prime. So if you increase your stress, the shear strength of that soil is not going to change. And if you reduce it, also that sigma prime is not going. That shear strength is not going to change. That is why we call sands stress dependent, and clays we call them stress independent. So the stress dependency of sands is basically related to the fact that they're granular soil. So if you have 2 grains, my knuckles are soil grains, the more you press them against each other, it increases the interlocking between soil grains, and that increases the strength. The other parameter that changes as you increase the stress is the elastic modulus. So not only now if you go back to this drawing here, that's ground surface, you have a sand specimen, you bring it to a lab, you do a triaxial test, so you apply a confining stress of sigma prime 3 all the way, vertical and horizontal, and then on top of that you apply a deviatory stress of delta sigma d, and you plot delta sigma d versus axial strain. And it turns out that the behavior changes as your sigma prime 3 increases. So if you're testing a sand under sigma prime 3 of 10 kPa, it will have an elastic modulus of that. And if you test the sand, lower this. And if you test the sand under sigma prime 3 of, give me a number. What, 30? 30 kPa, the elastic modulus, which is the stiffness of this line, increases. Okay, so now going back, why are we making this? Why are we even discussing this? Going back to the settlement calculation, we want to know what that E in the denominator of that equation is, right? That was the goal. But it's complicated because as you go deeper into the soil, the elastic stiffness of your soil increases. As you get shallower, the elastic stiffness decreases. So that basically describes why it's complicated to measure. But how do we measure it? How do we go about this limitation, or not limitation, but how do we solve this complexity? There are different methods to measure or estimate elastic modulus. One of them is, well, the options are lab testing, in-situ testing, and presumptive values. Let's look at lab testing first. Lab testing is when you take the soil, you bring it to the lab and test it. Turns out that it's not a very good way of calculating or measuring the elastic modulus of the soil. And partly is because sands are cohesionless, right? So when you sample them, you lose the in-situ characteristics of soil, including cementation, aging, and fabric in the soil. That's not the case about clays. Clays are cohesive, so when you sample them, you bring them to lab, they keep their characteristics because they keep all the particles and they keep the fabric together. But sands break apart, so once you bring it to the lab, it's a totally different soil. It's very different than what it was really in the ground. So measuring E from lab tests in sand does not provide reliable design values because it is very difficult, if not impossible, to get undisturbed samples in sand. Disturbed sample methods will lose infill, cementation, aging, and fabric. These are the three main factors that we lose when we sample the sand. Nathan?
I know we're talking about sands, but what about like a silty sand or a sandy silt running kind of right on the border? Is it possible to maintain undisturbed characteristics, or if you're taking a Shelby tube and a silty sand, you're basically just wasting your time?
That's a good question, and I think it depends, it changes case by case. It depends on the pI of the sand, of that soil. So for example, for Willamette silt, we've been very successful in sampling it.
Okay.
And the pI is for Willamette silt, let's say, in 10 to 20 ranges, but the ones that we've been testing are around 10. And even with the pI of 10, which is considered low plasticity silt, we still get a pretty good sample. You might change, you may go to a different silt with the same pI and be unsuccessful in sampling. But the general rule of thumb is that if you increase, the higher the pI of that soil is, it becomes more cohesive and it contains its fabric as you sample it. So you're more likely to get a good sample as you get to higher pI. Yes?
I have just a clarifying question. So the word fabric versus skeleton, you're talking about the soil structure? What's the difference?
It is. So skeleton we use to define the soil particles themselves, excluding the water and air. Fabric, we use the term fabric to describe the way particles are laid and deposited in natural deposition. So whether if they are wind deposited or water deposited, whether if they are alluvium or colluvium or all those different depositional methods, that changes the way the fabric is formed. And that's the one that you miss when you sample a sand and bring it to the lab, because all those little particles start to move relative to each other, so you lose that. Now, for those of you who had a seismic class, if you want to get an undisturbed sample in sand, can you remember of a way, an expensive way, but a way to get undisturbed sample?
Freeze it.
Freeze it.
All around it.
Freeze all around it, right. That's one way to do it, and it's very expensive, so you rarely do it in practice, but for research it's been done. You freeze it, and then you sample, push the tube into that frozen soil, then you bring it to lab, and then you can test it, and you can be almost sure that the cementation, aging, and fabric are retained. Good point. So that's about lab tests. Therefore, we do not use lab tests for measuring in sand. Next way of measuring or estimating elastic modulus is in sand is in situ testing. So if you're dealing with this limitation that we cannot sample, well, what about we measure it in the soil, keeping the soil there, lowering the device into the ground and testing it there. That's what we call in situ test. So again, the two main in situ tests that we discussed in this class are SPT and CPT, standard penetration test and cone penetration test. There is also PMT or pressure meter test. There is VS measurement. VS is a shear wave velocity. So shear wave velocity. We don't really get into the details of how we measure shear wave velocity in the field, but it's basically by sending a very small mechanical wave and measuring it at a different point and measuring how much time it takes for the wave to go from point A to point B, and that gives you the shear wave velocity of the soil. Turns out that we can use shear wave velocity to estimate the elastic modulus of the soil. Again, we leave that aside for other classes. So what if you don't have budget to do any of these? Or what if you're in phase 1 or phase 0 of your project and you want to get a rough estimate of your foundation settlement? Then the presumptive values come very handy. And in fact, we use presumptive values in codes a lot. Even when you're in the final stages of design, we tend to make sure use them as a sanity check. So even if you do a lab test or in situ test, we compare those results to presumptive values in codes to make sure that we're in a correct ballpark of numbers. So one of those examples is from Asheville RFT table C10463-1, which is the figure on the next page. And I'll talk about that in a second. But yeah, let's talk about that, and I'll go back to that last bullet item. So let's flip to page 11. This is that table in AASHTO. AASHTO is a code that we use for bridge design. So you have the type of soil on the left column. Let's focus on the top portion of this table. So then you have the elastic modulus, and then you have the Poisson's ratio. So for clays, Poisson ratio ranges between 0.4 to 0.5. It's an undrained behavior usually for clays, which means the water cannot leave or seep into the sample. And what is the Poisson's ratio of water from your mechanics, solid mechanics class? What is the range of Poisson's ratio? to 1? 0.5. 0.5 is the maximum Poisson's ratio that we can have, and it's an incompressible material. So water for the engineering loads, water is considered incompressible. So the Poisson's ratio of water becomes 0.5, and that is why for clays that behave undrained, their Poisson ratio is pretty close to 0.5 because the water cannot exit or enter the sample. And then you can look at the other soil. So if I pick sand here for loose sand, medium dense, and dense, that's the range of Poisson's ratio that we use. It's very typical to use 0.35 for sands if you don't have any other number. And so I'll give you these two values. For clays, Poisson ratio of 0.45, and for sands, Poisson ratio of 0.35. It's fairly typical to use. In the lower part of this table, there are some equations to be able to calculate or estimate elastic modulus using in-situ measurements. So these are using the N160, and if you do a cone penetration test, you can use QC to use here. One comment about QC and QT, I got some questions about corrected versus uncorrected tip resistance, and I want to clarify this. In all these equations that you use, assume that whether if it says QC or QT, assume that that is a corrected tip resistance. Okay? So this equation here, or the older equation, the correlations that we had in week 2, always assume that the QC or QT in that correlation is a corrected tip resistance, which becomes important in clays, but not that important in sand. Corrected tip resistance. Any question? All right, so that's a table for presumptive values for elastic modulus. So you can kind of see the range of values in KSI. For clays, it's 0.3 to 2, or goes, I guess, to 15. For sands, looks like it's a little higher, and that's reasonable. So clays are usually softer material compared to granular material. So I want to go back to that last bullet item on page 10. So one way to calculate settlement in sand is to use that general elastic equation. Measure, the load is given, so QB is given, the dimension is given. You can come up with those I1 and I2 factors. Let's leave that aside. But if you are able to estimate elastic modulus, then you can calculate yourself, right? That's one way to do it. The second way to do it is that, well, if I'm going to use in-situ tests, in-situ correlations to come up with elastic modulus, can I write my settlement equation to be directly related to the